The universe is a vast and mysterious place. We have made incredible strides in understanding its workings, but some secrets continue to baffle us. One such enigma is dark matter, an invisible substance that pervades the cosmos. It holds our universe together. Its gravitational influence shapes the distribution of stars and galaxies. Imagine a cosmic dance, a celestial ballet where galaxies twirl and pirouette across the vast cosmic stage. We see the dancers, the stars, and the galaxies, but an unseen force guides their movements. This invisible hand, my friends, is dark matter. Dark matter is like the wind. We can't see it directly, but we can see its effects. Just as the wind rustles leaves and propels sailboats, dark matter's gravitational pull dictates the motion of galaxies. It is the unseen choreographer of the cosmic ballet. Join me as we delve into the fascinating world of dark matter. We'll explore its discovery, unravel its properties, and uncover its profound influence on the universe we call home. Our story begins in the 1930s with a pioneering astronomer named Fritz Zwicky. He was studying the Coma Cluster, a massive gathering of galaxies bound together by gravity. Zwicky made a startling observation. The galaxies were moving far too fast for the cluster to hold them together. Zwicky's calculations showed that the visible matter in the cluster was woefully insufficient to account for the gravitational forces at play. He proposed a radical idea. Some unseen matter, which he dubbed Dunkel Materie, German for dark matter, must be lurking within the cluster, providing the extra gravity needed to keep the galaxies from flying apart. Zwicky's hypothesis was met with skepticism at the time. The idea of invisible matter dominating the universe seemed far-fetched. But as we'll see, his groundbreaking work laid the foundation for one of the most profound mysteries in modern astrophysics. Zwicky's observations of the Coma Cluster were like seeing a group of children playing tug-of-war with an invisible giant. The children represent the visible galaxies, and the invisible giant is dark matter. The children pull and strain, but the giant's immense gravity keeps them from breaking free. So what exactly is dark matter? Well, that's the million-dollar question. We know it's there, but its true nature remains one of the biggest mysteries in modern science. We call it dark because it doesn't interact with light. It doesn't emit, absorb, or reflect it. Think of a shadow on a sunny day. The shadow itself isn't a physical object, it's the absence of light blocked by something else. Dark matter is like a cosmic shadow, a region where the normal rules of physics seem to bend. Scientists have deduced the existence of dark matter through its gravitational effects on visible matter. We see its influence in the rotation of galaxies, the bending of light around massive objects, a phenomenon known as gravitational lensing, and the cosmic microwave background radiation, the faint afterglow of the Big Bang. Even though we can't see dark matter directly, we can infer its presence by observing how it affects the things we can see. It's like knowing there's a cat in a room because you see the toys moving even if you don't see the cat itself. Section 4. Sculpting the Cosmos. Dark Matter's Blueprint. Let's rewind the cosmic clock to the early universe, a time shortly after the Big Bang. Back then, the universe was a hot, dense soup of particles. As the universe expanded and cooled, gravity began to exert its influence. Here's where dark matter played a crucial role. Because it doesn't interact with light, it wasn't affected by the radiation that dominated the early universe. This allowed dark matter to clump together under gravity's pull, forming a cosmic scaffolding upon which the universe we see today would be built. Imagine a giant cosmic spider web. Dark matter forms the invisible threads of this web, creating a vast network of filaments and halos. These structures served as gravitational wells, drawing in the normal matter that would eventually coalesce into stars, galaxies, and galaxy clusters. Without dark matter's gravitational scaffolding, the universe would look vastly different. Galaxies would be more spread out, and the large-scale structure of the cosmos would be far less defined. Section 5. Galactic Choreography. An Invisible Conductor. Now, let's fast forward to the present day and explore how dark matter influences the movements of galaxies. One of the most compelling pieces of evidence for dark matter comes from the rotation of spiral galaxies like our own Milky Way. Stars in spiral galaxies orbit the galactic center much like planets orbit a star. However, astronomers have observed something peculiar. Stars farther from the galactic center orbit at roughly the same speed as stars closer in. This is unexpected, as our understanding of gravity predicts that stars farther out should orbit more slowly. This discrepancy between observation and theory points to the presence of a halo of dark matter enveloping the visible galaxy. This dark matter halo provides the extra gravity needed to keep the outer stars orbiting at their observed speeds. Imagine a merry-go-round. If you place objects at different distances from the center and spin it, the objects farther out should move more slowly, but if there's an invisible force pushing on all the objects equally, they'll all move at roughly the same speed, regardless of their distance from the center. That's essentially what we're seeing with spiral galaxies. Section 6. Vera Rubin's Legacy, Spinning Galaxies, and Dark Matter. The groundbreaking work of Vera Rubin in the 1970s solidified the case for dark matter's influence on galaxy rotation. Rubin meticulously measured the rotation curves of numerous spiral galaxies, confirming the puzzling observation that stars far from the galactic center were moving much faster than predicted. Rubin's meticulous observations provided some of the most compelling evidence for the existence of dark matter. Her work revolutionized our understanding of galaxies and cemented her legacy as one of the most influential astronomers of the 20th century. Her research showed that the visible matter in galaxies was insufficient to explain their rotation curves. There had to be something else out there, something invisible, providing the extra gravitational pull. That something, of course, was dark matter. Section 7. Unlocking the Secrets. The quest continues. The quest to understand dark matter continues to drive scientific inquiry. Researchers are working tirelessly to detect dark matter particles directly and unravel their properties. Experiments like the Large Hadron Collider are searching for signs of dark matter particles colliding with normal matter. The mystery of dark matter is a testament to the boundless wonders of our universe. It reminds us that there's still so much we don't know, and that the pursuit of knowledge is an endless journey. So, the next time you gaze up at the night sky, remember that what we see is just a fraction of what's out there. Lurking in the shadows is a hidden universe, a universe of dark matter, shaping the cosmos with its invisible hand.